Hi, we continue in this video chapter 5 about the derivatives and the differentiability, and let me recall what I said in the last video, that the derivative of a function f at a point a is defined as being the limit when h tends to 0 of f of a plus h minus f of a over h. Let's try to apply this definition on a particular function. Let's say, for example, let f of x be equal to x2, and we need to calculate the derivative of f at a point, let's say 3. So f prime at 3 would be equal to the limit when h tends to 0 of f of 3 plus h minus f of 3 over h, which is equal to 3 plus h. It's the limit. So limit when h tends to 0 of 3 plus h squared minus 9 over h, which is equal to the limit when h tends to 0 of 9 minus 9, it disappears, it cancels. Then we have 6h plus h squared over h, which is equal to the limit of 6 plus h when h tends to 0, which is equal to 6. So the derivative of f at the point 3 is equal to 6. If we look closer, this 6, it came from where? It came from this term in here, which is equal to 2 times 3, because it's the double product of the identity 3 plus h squared. It's 2 times 3 times h, right? And if you change the 3, if you calculate the derivative now, f prime at 4, it will be how much? It will be 2 times, it's the same thing, everything is the same, except in here we have 2 times 4 times h, which will lead at the end to 2 times 4, so it will be 8. And if you calculate the derivative f prime at a point, any point, let's say a, it will you will do the same calculation, and at the end we'll have to a. So until now, everything we did about the derivative and all the theorems we state, they were valid for the derivative of a function at a given point a. Now, since according to the definition we can calculate the derivative of a function at a point a, but we can calculate it at any point a, so we can have a formula that will give us the derivative at any point. So if you have, for example, the function x2, if you want to make the derivative at the point, let's say 10, no need to redo the calculation. You can use this formula, which gives you the derivative at any point a. So at the point 10, it will be the derivative, or the slope will be 20. So this is a formula that gives the derivative at any point. That's why we will say that if we take the function f prime of x equal to x, it will be a function that represents the derivative of f at any point x, and this is what we will call the function derivative. So the function derivative is a function of x that represents the derivative of f at each point. And to find it, we use the formula or the definition of the derivative to find a general form at a given point a. And this is the form that you studied in the last year for many functions, and all these forms were deduced from the definition of the limit as in here. So let f be a mapping. If f is differentiable at any point of I, we define the function derivative, and we denoted f prime as being the function that is defined from I into R, and which corresponds to each x the value f prime at x. So it's a function of x that gives the derivative at any point x. And we can prove the same theorems that were valid before at a point a for the function derivative. So we say that the function derivative of the sum f plus g is the derivative of f plus g that can be written f prime plus g prime, and etc. The derivative of lambda f is lambda times the derivative of f. The derivative of a product is f prime g plus f g prime, and etc. The one of the ratio 1 over g is g prime minus g prime over g squared, and f over g will be f prime g minus f g prime over g squared. As well, we can prove the same thing for the composite functions, saying that the derivative of g round f is g prime round of f of x, so of f times f prime. So it's the same results applied to the function derivatives. Now, of course, we can calculate also higher order derivatives. So we can calculate a second and a third and a fourth derivative, and etc. So let's denote first f with an exponent 0 between parentheses as being f. So then f exponent 1 will be equal to the derivative of f, and f exponent 2 will be equal to the second derivative of f, and so on. So this is what we are writing in here. If f is a differentiable mapping on I, and if f prime is differentiable, so the derivative of the derivative exists at a point A, then the derivative of the derivative at a point A will be denoted f double prime or f triple prime for the third derivative, etc. Then more generally, fn at A is the derivative of fn minus 1. So f3 is equal to the derivative of f2, etc. And the real number fn of A is called the nth derivative of f at the point A. So we call the nth function derivative of f the function fn of x. And we say that f is n times differentiable if this nth derivative exists on I. And we say also that f is infinitely differentiable if and only if f is n times differentiable on I for all n. So it can be as much as you want differentiable on I. Now we can prove similar results to the ones we got for the sum of the functions lambda times f for higher orders derivatives. So if you have a function that is written as the sum of two functions, then if these two functions are n times differentiable, then the function sum is n times differentiable, and the derivative of f plus g n is equal to the nth derivative of f plus the nth derivative of g. If also you have f n times differentiable, then lambda f is n times differentiable, and the nth derivative of lambda f is equal to lambda times the nth derivative of f. It's also true for the product and for the ratio, but for the product and the ratio the formulas are more complicated, because the nth derivative of the product is written as the sum from k going from 0 to n of cnk fk, so it's the kth derivative of f times the n minus kth derivative of g. So it's like if you calculate fg third derivative, it will be cn0 f0, so it's f g third derivative, plus cn1 first derivative of f second derivative of g, plus cn2 second derivative of f first derivative of g, plus cn3 third derivative of f and times g, and n in this case is equal to 3. For the ratio we don't have a formula, but we can conclude that it's also n times differentiable when f and g are n times differentiable. Now if f is n times differentiable and all its derivatives are continuous, then we say that f is a Cn function, or it's in the class Cn. So again, it means that f is n times differentiable and the derivatives are continuous on I. Of course, it's sufficient to say that fn is continuous on I. It means that all the derivatives are continuous on I, because of course they were differentiable, so they were continuous. But the last one if the function is Cn, it means that it's n times differentiable. So since f1, f2, f3 are differentiable, so they are continuous, but we know nothing about the last one, fn, so at least it should be continuous, so the function can be in Cn. We say also that f is C infinity if it's infinitely differentiable on I, which means also that all the derivatives are continuous. We denote by C0 CIR, so f belongs to CIR. If it's C0, it means of class C0, so it's at least continuous. We know nothing about the derivatives. And also a mapping f can be n times differentiable without being a Cn function if the nth derivative is not continuous. We can also prove similar results as in the last theorems. We say that if f and g are Cn functions, then f plus g is a Cn function on I, lambda f is a Cn function of I, f times g is a Cn function, and f over g as well. And also for the composite functions, if we have f and g satisfying the hypotheses of the composite functions, so f is defined from I into R, g from j into R, and f of I is included in j, then if f and j are Cn, then g round f also is a Cn function on I. We need to state now three very important theorems that can be applied to continuous and differentiable functions. The first one is the Rolle's theorem. It says that if you have a function f defined on AB into R, so if it has the three following hypotheses. First, f is continuous on the closed interval AB, s is differentiable on the upper interval AB, and f of a is equal to f of b. It means that you have a function like this. So it takes values, it's continuous and differentiable, and there is a point A where f of a is equal to another image of a point B. So you have f of a is equal to f of b. Then there exists a point C that belongs to AB, so it's in here inside, such that the derivative of f at the point C is equal to 0. It means that the slope of the tangent at f at this point C is equal to 0. So the tangent is horizontal, it's parallel to the x-axis. So it means that they are talking about this point in here, where the tangent is horizontal. Okay, so you cannot have a function that is continuous and differentiable on AB taking the same value at two different points A and B without having a point where the tangent is horizontal. So if the function passes by a point A and then it passes by a point B where we have the same image, then of course there is a point where the function turned down to go down, or if it was decreasing, it will turn up and go up to pass by the same value. It means also that, for example, if you are driving a car, okay, and if you are driving a car on a straight road, and let's say you cannot turn around, you can, like, if you want to go backwards, you have to stop and go backwards, okay? And then if you're driving this car and you pass by a shop, and then you want to pass by this shop another time, it means that at some point you have to stop and go back to this shop. So it means that at some point your velocity will be 0. It's where you stop and then you go backwards. And the velocity is the derivative of the function displacement. So it's the same thing. It says that the derivative at a point, it should be 0, so you can pass by the same place one more time. Now watch out, this C is not necessarily unique. So you can have many point C's where the function derivative, or where the derivative is equal to 0. But the theorem states that at least there is one C where the derivative or the slope is horizontal. Now be careful that in some books you may find the Rolle's theorem stated like this. It can be rewritten as I mean the last part where we say that there exists a C such that it can be written as there exists theta between 0 and 1 such that f prime of a plus theta b minus a is equal to 0. Why it's the same thing? Because when you say that C is between A and B, it means that C can be written as this kind of combination. Because if theta is between 0 and 1, let's take for example theta equals to 0. This value A plus theta B minus A in here will be equal to A. And if theta is equal to 1, this value will be equal to B. And if theta is between 0 and 1, then this value will be something between A and B. So the expression A plus theta B minus A represents all the points starting from A, finishing in B, and all the points between A and B. So it's the same thing as saying that there exists C between A and B, satisfying f prime of C is equal to 0. Now, the second theorem we are stating is the mean value theorem, which is widely used in many places. It says that if you have a function f that is also, as in the Rolle's theorem, it's also continuous on the closed interval AB and differentiable on the open interval AB, and without any given on f of A and f of B like in the Rolle's theorem. So it means that it gives that there exists a point C between A and B such that f of B minus f of A is equal to f prime of C times B minus A. Or it can be written also f of B minus f of A over B minus A equals to f prime of C. Now, to prove this theorem, even though it seems that the Rolle's theorem is a particular case of this one because it has the same given but with one additional hypothesis, so it gives the impression that the Rolle's theorem is a particular case of this one, but to prove this theorem, we will use the Rolle's theorem in fact. So we take a function phi such that phi of x is equal to fx minus f of b minus f of a over b minus a x, and we notice that phi is continuous and differentiable, continuous on the closed AB and differentiable on the open set AB. And we notice also, if you try to replace x by a and by b, you will notice that phi of a is equal to phi of b. So the hypotheses of the Rolle's theorem can be applied in here, or are valid in here. Therefore, using Rolle's theorem, there exists C such that phi prime of C is equal to 0. So if you calculate phi prime of C and you put it equals to 0, you will have the result of the Rolle's theorem. So try to do it at home. It's very interesting. So we used Rolle's theorem to prove the mean value theorem. But what does the mean value theorem really means? It means that if you have a function that is continuous and differentiable on AB, let's say this is A and this is B, then you can find a point C such that f prime of C is equal to f of B minus f of A over B minus A. So what is f of B minus f of A over B minus A? It's the slope of this straight line going through the points A f of A, B f of B, right? So there exists a point C where the slope is equal to this slope. It means that there exists a point C where the slope is parallel to this straight line. Okay, so this is the meaning of the mean value theorem. It means that if you are driving a car, let's say, then if you calculate, you go through 2 points, point A and point B, and then if you calculate the difference between f of B minus f of A divided by the difference between B and A, which will give this will give the mean value of the velocity between these two points. Okay, then there exists a point between these 2 points where the velocity was equal exactly to the mean value of the velocity. So let's say, for example, if you are running 20 in here, 20 kilometers per hour, and then at some point you were like 100 kilometers per hour, then if you calculate 100 minus 20, the difference, the mean value of the velocity, it will be equal to some value. Then of course this value was reached somewhere on the road. So you cannot have a mean value of the velocity without having at least at one point this value of the velocity running at this value of the velocity. This is of course true because the velocity will change in a continuous way. The function is continuous. If in the class, for example, you take the grades of the students, you might have the mean value of the grades equals to 10, for example, without having one single student having a 10. If all the students have like, let's say you have 50 students with 9/20 and 50 students with 11/20, then the mean value of the grades will be 10, but you don't have any single student with a 10 with a grade equals to 10, because the grade distribution is not continuous. You have discrete points. So the mean value theorem is applied only when the function is continuous. Now this mean value theorem can be generalized into this form. If you have two functions f and g, continuous and differentiable on AB, and if you suppose that g prime is never equals to 0, then there exists c on AB such that f of b minus f of a over g of b minus g of a is equal to f prime of c over g prime of c. Now everything we studied is very interesting to be used to study the variations of the functions. So to see how the functions can increase, decrease, or how can they present maximum or minimum points. So let's take the first result. If I is an interval of R, then if f is continuous on I, differentiable on I, and if for all x in the interior of I, this is the interior of I, and when we say interior of I, it means all the points in I without the points at the boundaries of the interval I. So if at the interior of I, f prime of x is equal to 0, so the derivative is always equal to 0, then f is constant on I. Why is that? Because very simply, if you take 2 points in I, let's say x1 and x2, such that x1 is less than x2, and if you apply the mean value theorem to the function f between the points x1 and x2, then you will have f of x2 minus f of x1 equals to f prime of c. I mean there exists c between x1 and x2, such that f of x2 minus f of x1 equals to f prime of c times x2 minus x1, but since f prime is equal to 0 at any point, so f prime of c is equal to 0, so this will be equal to 0, and f of x1 will be equal to f of x2, so f will be constant. We can prove as well that if f is continuous and differentiable, then we have the equivalence between f increasing on I and f prime of x is positive for all x in the interior of I. This is not easy to, this is not difficult to prove, because to prove the first implication, we can take as a hypothesis that f is increasing on I, and let x be in I and h be in R star, such that a plus h is also in I. Okay, so we have 2 points in I, x and x plus h. Here you should have x plus h, in fact. Then the ratio f of x plus h minus f of x over h will be positive, of course, because f is increasing, and since x plus h is greater than x, then f of x plus h minus f of x is positive. So going through to the limit when h tends to 0, the ratio will remain positive, of course, and this will prove the first implication. For the second implication, if you have f prime of x positive, then using the mean value theorem on 2 points x1 and x2, such that x1 is less than x2, will allow us to say that there exists c between x1 and x2, such that we have this equality. But since we know that this is positive because x1 is less than x2, and this is positive because f prime is greater than 0 for all x, f prime of x, then the product is positive, then f of x2 is greater than f of x1. So x1 less than x2, then f of x1 less than f of x2, which means that the function f is increasing. Of course, we can prove similarly, or by replacing f by minus f, that if f is decreasing, it's equivalent to say that f prime of x is less or equal than 0. Let's define now the extremums of a function f. So we say that f has a local maximum or a local minimum at a point A if there exists a neighborhood n of A such that any point in this neighborhood, it has its image less than the image of A. So it's like if you have like this, even if the function will go higher at some points far away, but at this point, for example, at this point, you can find a neighborhood of A such that all the points in here, they have their values less than f of A. It means that at this point A you have a local minimum. It's not a global, local maximum. It's not a global maximum. It's a local maximum because it's valid only in a neighborhood around this maximum. So it's also valid for the minimum, and we say that f of x is less than f of A for any x in the neighborhood, or for the minimum it applies as well. And we say also that f has a strict local minimum if this inequality is strict. So in the first inequality you might have something like this and it becomes like horizontal and then it goes down. This is a local maximum which is not strict because you have values having the same value as this maximum in any neighborhood you choose around the maximum. Okay, but when it's strict, it means that all the points, they have their images strictly less than this maximum or strictly greater if it's a strict minimum. We say that f has an extremum at A if it has a maximum or a minimum at A. Now we can prove a very interesting result saying that let I be an interval of R. We have that if A belongs to the interior of I, f differentiable at the point A, and f has a local extremum at A, then of course f prime at this point will be equals to 0. Let me point out two extremely important points in this theorem. First, we have the implication that says that if f has a local extremum, then f prime of A is equal to 0. That's great. But we don't have the converse. We don't have the other way around. So if f prime of A is equal to 0, it's not necessary to have that f has a local extremum at A. So we might have points where the derivative is 0 without being local extremums. This is the first point. It's like the function x3, huh? It goes like this. So at this point the slope is horizontal, the derivative is 0, but this point is not a maximum at all. Also, another thing is that it's very important to notice that we are talking about points in the interior of I. It means we are not talking about points that are at the extremum or the boundary of I. Because if you have a point at the boundary, if f is defined, for example, between a value a and b, so f is doing like this, okay? So at the point b, you have a local maximum, but the derivative at the point b is not equal to 0. Okay, so if you are at the boundaries, this theorem does not apply. It applies only if you are inside the interval. Now to prove this, let's prove it for the local minimum at A. So if A presents a local minimum, then if you take A plus H, any A plus H around A, you will have f of A plus H minus f of A, what's in here, positive. And if H is positive, then the ratio will be positive. And f of A plus H minus f of A in here, it's positive. But if H is negative, then the ratio will be negative. So if you go to the limit, you will obtain that f prime of A is equal to 0. Because you will have f prime of A on both sides, but one is positive and the other one is negative, and they should be equal. That's why f prime of A will be equal to 0.